Thank you. Good afternoon. I'm Hamed Okravi, a senior staff member at MIT Lincoln Lab, and today I'm going to present the result of our work in evaluating leakage-resilient diversification techniques. This was joint work with our colleagues at MIT Lincoln Lab and also collaborators from Immunant, the University of California, Irvine, TU Darmstadt, and University of Duisburg-Essen in Germany. I'm going to show you the bottom line of this presentation up front so that you know what to expect. Code diversity techniques are vulnerable to information leakage attacks. And because of that, there has been a recent development of leakage-resilient techniques. So one approach to do this is to leverage execute-only permission on memory so that these techniques prevent leakage of information. We present an attack that can generically bypass these defenses. It's called address-oblivious code reuse attacks, AOCR. And we present 3 real-world exploits. So before we describe the technique, let's look at the type of attacks that are the focus of this work. These are memory corruption attacks. Many of you are familiar with them. There are 2 different types of memory violation. There are spatial memory violation, in which an attacker writes past an object, the bounds of an object, and overflow into adjacent areas. A typical example is a buffer overflow attack, in which the attacker overflows a buffer and overwrites function pointers, for example. And the second type is a temporal memory violation, in which an attacker uses dangling pointers, for example. In this case, an object is allocated on the heap. Later on, the object is deallocated. But if there is a dangling pointer pointing to that region of heap, if later on we store a function pointer there, an attacker can overwrite that function pointer and hijack control of the application. Code diversity techniques are designed to mitigate this type of attack. And there are many of them that exist or that have been proposed or exist in reality. There are ones that are load time randomization, for example, address space layout randomization, as was described in previous talks as well, which randomizes the location of certain regions of memory, such as heap, stack, and link libraries at load time to random addresses. There are other techniques, for example, compiler-based diversity techniques that take a source code and create diverse set of binaries from the same source code so that the binaries don't look alike. There are diverse binaries. And there are also runtime randomization techniques that take a binary, run it through a diversifier, and create a diverse set of binaries by replacing certain segments of the code with equivalent but different instructions. Now, diversification only works if information can stay hidden from an attacker. Unfortunately, that's not the case in reality. There are information leakage attacks that can leak to an attacker how the system has been diversified. And that way, an attacker can bypass these defenses. One type of information leakage is direct memory disclosure, in which an attacker reads exactly how the code has been diversified. For example, there is buffer overread vulnerabilities. These are similar to buffer overflows, in which an attacker reads past the buffer, and that way they can leak parts of the code and know exactly how the code has been diversified. There are also other types. Indirect memory disclosure is the other type. If we randomize the location of code snippets or code segments, that is good, but there are also pointers to those code regions. For example, there are function pointers and return addresses that are stored on the stack. So by leaking those values, an attacker can learn exactly where those code snippets are and attack them. So this is the motivation behind leakage-resilient diversity techniques. Now, in order to describe those techniques, let's first take a quick look at how memory permissions work. In a typical memory, we have data regions that are readable and writable, and we have code regions, which are executable, of course, but also they're readable, because in modern architectures, there's just 1 bit for memory permission. So it can be either readable and writable, or readable and executable. An observation that's made by a class of leakage-resilient diversity techniques is that we don't really need the code to be readable. If we make the code executable only, we can prevent direct leakage of information. So in this case, the code is marked as executable only. The data region is still readable and writable. And because of that, these techniques can prevent direct leakage of diversified code to an attacker. So this would prevent a typical buffer overread vulnerability. This type of permission is either enforced in software or using shadow page tables and leveraging virtualization features of the processor. So this would prevent direct leakage. But in order to prevent indirect leakage of information, indirect memory disclosure, things become more complicated. As I mentioned, we have these function pointers in the data region that point to the diversified code. So to deal with this type of indirect leakage, these techniques use various tricks, various obfuscation or indirection tricks. One popular way of doing this is adding an extra layer of indirection. So in this case, the function pointer is replaced with an indirect code pointer. And what that points to is sort of a snippet of code called a trampoline, which itself jumps to the actual code. So now we have this extra layer of indirection, and this part, the executable part, is completely invisible to an attacker. So now if the attacker leaks the indirect code pointer, they only learn the location of the trampoline and not the actual code. And of course, the trampoline and the code itself are placed at random addresses in that executable section. I have to emphasize that the trampoline is also itself in executable only section. Now, if we think about it, what this technique is doing is essentially enforcing certain entry points and exit points to the diversified code. So it allows certain ways of entering that code. In essence, that's a form of coarse-grained control flow integrity. So it creates a surrogate for accessing the code. That indirect code pointer is a surrogate of the code. So there are a number of research questions that come from this type of technique. The first one is, can an attacker reuse code at the granularity of those indirect code pointers and implement an entire malicious payload just based on those? And if so, can they accurately find out or identify which functions those indirect code pointers correspond to? And can they chain them together in order to build complex payloads? In this work, we show that the answer to all those three questions is yes, unfortunately. So the first step in mounting this type of attack is identifying what each indirect code pointer, what function each indirect pointer corresponds to. And the way we do that is by running a local copy of the target application. So let's say this is a web server and we want to target it. We run a local copy of it, and we send queries to it as we do normally. And then we observe that certain function pointers, for example, in this case, a pointer to open, will be stored on the stack. Now, the real target is the remote attack, the remote application that is protected by these leakage-resilient techniques. Now, the executable part of it is completely oblivious to us, but we can still observe the data segment of that code. So by using information leakage, we can learn that an indirect code pointer is stored on the stack of the remote application. Now, by observing that, in this case, the function, a pointer to open is stored on the stack. In that case, an indirect pointer, code pointer is stored on the stack. The attacker can observe that these two values are really the same thing. So that indirect code pointer is essentially the same thing as having a pointer to that function open. So this way, we can map what indirect pointers correspond to what real functions in the application. So this is saying that, in essence, running the application itself leaks enough information that we can infer or reverse engineer that layer of indirection. Now, note that I mentioned that the trampoline and the diversified code is randomized, so that those are at random locations. The code itself can be diversified even with finer grain randomization. So even at the instruction level, it may be randomized. It doesn't matter. As long as that indirect code pointer, ICPR, exists on the stack, I can still reach the function that I'm interested in by reusing code at that level. That's why we call that an address-oblivious code reuse gadget, AOCR gadget, because it's completely oblivious to what type of randomization is happening in the rest of the application. Now, you might ask, okay, a running application, you want to identify a pointer on the stack. These things change very rapidly. Can we accurately identify which code pointer is stored at what stack location? Is this too volatile? In fact, we have developed a technique called malicious thread blocking that can be used to accurately identify these indirect code pointers. In this case, assume that we have two threads in the application. So normally these two threads execute, and maybe you have a mutex that thread A sets to lock the application. Thread B waits there until the mutex is released. After it is released, they both proceed execution. But if an attacker can force thread B to set the mutex maliciously, it can force the thread A to pause there indefinitely. And by sort of maliciously blocking the thread, an attacker can create a stable version of stack that they can easily profile. So by doing this, we can pause the application momentarily so that we can identify indirect code pointers accurately. And then the last challenge is chaining these things together, chaining AOCR gadgets together. The challenge here is that these are unlike ROP gadgets. We cannot just put their addresses on the stack and execute them one by one, because when they return, they go back to the original call site because of this layer of indirection that exists because of the trampolines. So we have to somehow exploit the benign semantics of the code itself to chain these gadgets together. In order to do that, we have developed a technique called malicious loop redirection. It exploits loop structures like this, which are very common in applications. It loops over a task, calls a function pointer on each task, and then goes to the next task. So in this case, what would be stored in the data memory are those tasks with their function pointers and arguments and pointers to the next task. And then the function pointers point to function trampolines. What we can do in order to chain our AOCR gadgets together is to overwrite those pointers to now point to the functions that we are interested in. In this case, open and write, so that we can open a file and write to it. As you can imagine, this would be quite malicious. And then the next pointer of the last entry would point to the first task, so that now we have created a loop that calls these AOCR gadgets one by one without actually breaking the semantics of the program. So this would properly return to the same call site and loop back. So this way we can chain these AOCR gadgets together and implement arbitrary malicious functionality. We have created a proof of concept exploit against Nginx. There are many details involved in it, so I refer you to the paper for all the details. At a very high level, there are 4 steps into this exploit. We locate a mutex in Nginx that can be used for malicious thread blocking. And then we profile an indirect code pointer for function open. And then we profile another indirect code pointer for writing to a file that we can open. And then we corrupt Nginx's task queue in order to call these AOCR gadgets one after another and implement the malicious behavior using malicious loop redirection. We have also created another exploit against Nginx and one against Apache. All the details are available in the paper. Now, if we look at the recently proposed leakage-resilient techniques, here are the rows. And attacks that I described, the first column and the third column are direct and indirect memory disclosure. The last column is the attack that I just described, AOCR. And the second column relates to an implementation challenge of these techniques that I didn't go into for the sake of time. That is quite hard to mitigate. So these 2 columns are novel contributions of this work. As you can see, there's a lack of coverage in that area. Many of the techniques are vulnerable to this type of attack. The last row, if you're curious, is a re-randomization technique that's not vulnerable to this particular type of attack, but it has its own caveats and limitations. I refer you to the paper for the details of that. So how can we mitigate this type of attack? Of course, complete memory safety would prevent AOCR attacks. So that's one solution, of course, given that the performance overhead would be acceptable. AOCR attacks are oblivious to addresses in the code, but they're not oblivious to data. So if we randomize the data, it's going to break this type of attack. And last but not least, if we can implement some sort of authentication on indirect call sites so that we have tokens there and check the token to ensure that we go to the proper indirect call site, this would also prevent this attack that I just presented. This technique would be very similar to cryptographically enforced control flow integrity technique, CCFI, that was published at CCS last year. To conclude, code pointers pose a major challenge to leakage-resilient techniques. We presented a generic type of attack called AOCR that can bypass these techniques, and we presented ways to accurately perform the profiling and also chain these gadgets together. And the major lesson from this work is that effective defenses should leverage aspects of diversification and enforcement-based defenses for them to be effective. Thank you for your attention. I can now take questions.